back to this video series on trees and tree-based data structures. In this second part, we'll cover a basic tree implementation in Java and develop several tree traversal algorithms that allow us to enumerate and process the nodes in a tree. Before we develop any algorithms for trees, we need to understand how to implement a tree data structure. To illustrate the basic ideas, we'll design a simple binary tree in Java. To do this, we first need to design a tree node class that stores elements that we want to store in the nodes, as well as references to its left and right children. For convenience, we'll also include a reference to the node's parent to enable traversing up the tree. We'll also include several convenience methods. Finally, we'll use this node class in a binary tree implementation that simply stores a single node reference to the root. First, I'll create a tree node class and parameterize it so that it can hold any type of element. Next, we'll add the state of the class as previously described. Now let's add a constructor and several getter and setter methods. Now let's add some convenience methods that allow us to determine the relative connectivity of nodes. Now to create the tree implementation that uses this node class. All we need is for the class to hold a reference to the root node. That's good for now. We'll follow up with more methods later. Before we start developing trees into general purpose collection data structures, we need a way to ensure that all the elements that we store in a tree can be enumerated. To that end, we'll develop several tree traversal algorithms and strategies that allow us to process each node in some manner. Since a tree has only a reference to the root, that is always the natural place to start. However, unlike a linked list, which only has one direction to traverse, we have several options. At a current node, we could go to its left child, right child, or to its parent as a next choice. More importantly, how do we remember what our choice was so that we can return and visit the other nodes? To develop this idea, let's think locally with a simple example. Given a simple 3-node tree, we could enumerate or process each node in one of 3 orders: root, then left, then right, left, then root, then right, left, right, then root. You may notice that there are actually 3 additional permutations of these 3 orderings, each that visits the right node before the left node. We won't consider those, however, as they would be equivalent to one of these 3 orderings on a mirror image tree. The first option, where we process the root node first, then the left, and subsequently the right child, is known as preorder traversal. The other 2 options simply change when we process the root, between the left and right, known as inorder, or after both, known as postorder. This can easily be generalized to consider a left subtree and a right subtree, rather than just a left and right node. We'll explore all 3 of these traversal strategies and more, but we'll start with preorder. We have a small binary tree. Let's run through the ordering to get the basic idea, and then we'll develop an algorithm that codifies this process. We'll start at the root and process it before visiting its left subtree and right subtree respectively. Next, we traverse to its left child and immediately process it. We then traverse to D and process it. Now that we process B and B's left child, we finally traverse to its right child and process the subtree rooted there. At this point, we're done with A's left subtree, so we continue to its right subtree and process C. And then finally F. The pre-order traversal of this tree was A, B, D, E, C, F. To develop an algorithm that implements this idea, we need a way to remember that there are right children and right subtrees that we need to return to process after processing the left children and its left subtrees. Not only that, but as we saw, right children and trees deeper in the tree need to be processed first before returning to those that we skipped shallower in the tree. Since we start at the root, we need a way to remember the most recently encountered right children in trees. That is, we need a way to keep track of where we've been, or breadcrumbs, so to speak. A stack-based data structure gives us exactly what we need with its LIFO ordering. Let's develop some pseudocode that codifies this idea. The input will be a binary tree T, and will output a pre-order traversal of its nodes. First, we initialize an empty stack. Then, as a starting point, we'll push the root onto the stack. We'll need a way to continue our algorithm until all of the nodes have been processed, so we'll continue executing while there's still nodes to be processed in the stack. You can view the node at the top of the stack as the current node, so the first thing that we do in our iteration is that we'll pop it off, and process it. Now we need to set ourselves up for the next iteration of the algorithm. Specifically, we need to push the current node U's children onto the stack so that we can process them in a future iteration. We have to be careful with the ordering, however, since the stack is LIFO. We push first the right child, and then the left child, so that the left child will be the next node to be popped off the stack on the next iteration. To understand this algorithm better, let's step through it line by line with our example. First, we initialize the stack. Then we push the root. On the first iteration, we pop A and process it. We then push its right and left child. On the second iteration, B is popped off the top of the stack and processed. And then we push its children. The third iteration processes D. However, D has no children, so the two push operations have no effect. The next iteration pops E off the top and processes it. Likewise, E has no children, so the push operations have no effect again. The next iteration pops C off the stack, returning to A's right subtree. We then push its right child, but there is no left child. The final iteration of the while loop pops and processes F. The stack is finally empty and the algorithm terminates. Let's implement this in our Java class. We'll adapt the algorithm by translating the pseudocode. Ultimately, we'll be returning a list containing the node data in the preorder enumeration. I've recreated the example tree that we were using in our demonstration to test the method. For our stack, we'll use the preferred deck data structure in Java. In our pseudocode, we have an implicit behavior that null nodes are not pushed to the stack. In Java, we'll need to be more explicit with our null pointer checks. Let's test our implementation to see if we get the same results. And we do. A, B, D, E, C, F. Next, we turn our attention to an in-order traversal, which visits nodes in a left, then root, then right order. Let's demonstrate an in-order traversal of the same tree. Again, we start at the root, but we do not immediately process it, represented here in blue. Instead, we'll remember that we have to come back to it after we've processed the left subtree. We then traverse to the left child, but again we don't process it yet. Then we traverse to D, and there is no left child, so we go ahead and process it. We then return to its parent B and process it, and then go to its right child. Again, since it has no left child, we proceed and process it and return. Now that we've processed A's entire left subtree, we can process it and proceed to its right subtree. Since C has no left child, we process it and proceed to the last node, F. An in-order algorithm uses the same basic idea as preorder. We use a stack to keep track of nodes that still need to be processed. However, we don't process them right away. We wait until we've explored the left subtree. But we need a way to tell that if we're encountering a node, is it the first time or the second time that we visited it, so that we can process it properly on the second time. To do this, we'll still use a variable to keep track of the current node, but we don't push its children. We push the node itself and move on to the left subtree. Here's the full algorithm. Our initialization sets the variable u instead of pushing it to the stack. Our continuation condition likewise is different, as we'll see in a bit. We have two blocks of code in our loop, one to handle the case when they're visiting the node for the first time, and the second for when we encounter it the second time, and process it. The first block pushes the current node under the stack for later processing, and moves on down to the left subtree. The second block pops the node, processes it, and moves on to the right subtree. Again, let's walk through the algorithm with the same tree. We initialize the stack and the current node. On our first iteration, the current node u is not null, so we push it onto the stack and move to its left child. Likewise, on the next iteration, we push b and move to the left child. On the third iteration, we still push d, but when we move to the left child, it becomes null. This sets us up for the next iteration. Since the current node u is null, the second block now gets executed for the first time. We pop d from the stack and process it, moving to the right child. Again, it sets the current node to null, so that on the next iteration we pop b and process it. Now we move to b's right child and continue. We push it, and the left child becomes null. The next iteration pops and processes e. The absence of a right child sets us up for returning to the root on the next iteration. We pop and process and move to the right child. On the next iteration, the importance of the second condition in our while loop becomes apparent. The stack is empty, but we're not done. We push C onto the stack and move to its left child, which is null. The next iteration pops and processes C, moving to the right child, F. We push and process it on the last iteration of the loop. Since the stack is now empty and u is null, the algorithm terminates. Let's implement this in Java. Let's go ahead and test it. If it works, we would expect D, B, E, A, C, F. And it works. Our final traversal strategy is postorder, in which we visit the left and right before we process the root. Here's a demonstration. We start at the root and then traverse left, and then left again. Since there is no left child nor right child for D, we process it. We return to B, but we don't process it right away. Instead, we go to its right child first and process it. And since E has no left or right child, we go ahead and process it. And then finally process B. We return to the root, but descend to its right tree before we process it. C has no left child, so we go to its right and process it. We then return to C and process it, and finally last A. In any post-order traversal, the root node is always the last thing to be processed. This algorithm is a bit more complicated. We need to distinguish between three cases, whether it was the first, second, or third time that we visited the node, so that we can process it on the third and last time. To do this, we need to keep track of both a current node and a previous node, so that we know both where we are and where we came from. Here's the full algorithm. Since we're keeping track of more information, there's a lot more corner cases to handle. We'll omit a line-by-line demonstration, but more details and resources are available on our website. An analysis of all three traversal strategies is pretty straightforward. For our elementary operation, we could count either the number of times a node is traversed, or the number of times that a node is processed. In either case, the complexity is linear with respect to the number of nodes. There are also numerous applications to each of these traversal strategies. Preorder traversal is the simplest and most straightforward traversal algorithm. It can be used to perform many basic operations in trees, but also by compilers when evaluating expression trees in prefix notation. Inorder traversals can be used to produce a sorted enumeration in a binary search tree, which we'll be examining next. Postorder traversals can be used in topological sorting of graphs, deleting trees, and when using postfix notation in many languages, such as PostScript and PDF. All of our implementations have used an in-memory stack as their core data structure. Alternatively, many treatments of tree traversal strategies use recursion, as it is arguably simpler code. The base case is the same in all three instances. If the node that we're given is null, we simply return. Otherwise, we make two recursive calls on the left child and the right child respectively, but not before we've processed U. This gives us preorder traversal. The simplicity comes when we see the difference between the three algorithms. In an inorder traversal, the only substantive difference is that we process the node between the two recursive calls instead of before. And for a postorder traversal, it's after. This recursive code is seemingly simpler, but as with all recursion, it does have its pitfalls. In our presentations, the stack was useful to keep track of breadcrumbs and where we came from. However, binary trees are highly structured, so we only need to keep track of local information rather than the entire sequence of vertices that we traverse to get us there. In fact, we only need to keep track of where we are, the current node, and where we came from, the previous. All three traversal strategies were actually the same in how they traversed the tree. We basically walked around the perimeter of the tree. They only differed in when we processed the node. Preorder if it was for the first time that we visited, that is, coming from the parent. Inorder if we were coming from the left child. And postorder if we were coming from the right child. This gives us some very simple rules for traversing or walking around the tree, and when to process the node for each of the three strategies. We omit the pseudocode here as it's rather complicated because of the number of corner cases that we need to handle. The key idea, however, is that all three traversal strategies are possible without the use of an external data structure. This means that we can perform traversals with limited extra memory in applications where resources may be constrained. Yet another traversal strategy is breadth-first search. Preorder, inorder, and postorder are all variations on depth-first search because they traverse as far down into the tree as possible before exploring other areas. The alternative is to explore shallower in the tree before going deeper. Given the orientation of trees, this provides a top-down, left-to-right enumeration of the nodes, as depicted here. In other words, the nodes are processed as if we were reading a book. Here's the full algorithm. It may look very familiar. In fact, it's nearly identical to the stack-based preorder traversal that we developed earlier. Here they are side by side. The only difference is the data structure that we use, a queue instead of a stack, as well as the order in which we handle the left and right children. This is a quintessential example of the power of smart data structures. The same simple code provides fundamentally different behavior when we use different data structures. This calls back to one of our major themes, that smart data structures and dumb code are a lot better than the other way around.